think was definitely the most straightforward problem of the contest. So we basically have like I think honestly the trend I've been observing with USACO contests this year is there's always like this it's if it's every I think every single contest follow the same three trend, which is the first problem is implementation problem. The second problem is like an array kind of problem. And the third problem is like it was always the hardest, like some kind of ad hoc with like some additional things. But yeah, this is the implementation one. I think this one wasn't too complicated to think about. So basically, quick summary of the problem statement. We have n different symbols, and there's just like this n by n chart. Well, it's not given as an n by n chart because like it would be just overlapping, but it basically is like an n by n chart which shows for every single pair of symbols how they interact with each other, right? So, it either when you have a pair of symbols, either one of them beats the other or they draw against each other. It's kind of like rock or scissors, but there's like a lot more symbols. So now, the catch is that there's going to be each time they play two symbols, and you basically want so Elsie we know exactly which symbols Elsie's gonna play, and we want Bessie to have symbols such that no matter which symbol that Elsie picks in the end out of her two ones symbols, Bessie can pick a symbol and be guaranteed to beat Elsie. So, this seems kind of convoluted. Like the problem statement might take a while to like, wrap your head around. But in reality, like all this really means is that okay, so let's say like Elsie picks two symbols. I don't know, like picks let's say like one and two. Actually, I should probably just let me just use this drawer instead. So let's say Elsie picks like one and two, right? Right. We just need a Bessie to have one symbol that can beat, let's say like symbol X that can beat both one and both beat two. Because we don't actually know which one Elsie's gonna pick, and so the only way to guarantee that Bessie can win is if she has this symbol X that beats both. Now, how do we find the symbol X that beats both? I mean, there's a lot of ways we can do this, right? So, I mean, we have the entire table of which ones, and we see here that, N and M are both less than 3,000. So when you see this, then you know that, okay, we can just, for every single M, right, M, we can do N queries. So MN works, right? O of NM. So that means that we just need to do this in O of N for each LC symbol pair. And that's pretty straightforward, right? Because all we need to do, we can just loop over LC's first symbol, LC's second symbol, and find the overlap. Like basically find how many numbers X beat both of them, right? And we know that as long as Bessie has one of them, one of Bessie's hands is good. Um, But now, in order to find every single possible pair that Bessie can have, we need a little bit of math. So let's denote, let's call, I don't know, let's say K. K is equal to the number of X that can beat both, that beat both LC symbols. Right, let's call this K. So it'll be like basically the number of X's here that can beat both of them. So we need to find the number of hands that work. We obviously every single hand that works obviously has to have at least one of these X's, right? This we already established this because it has none of them, right? Then we can't guarantee it beats both of these. So to finish this off, we just need a little bit of math, a little bit of combinatorics, right? So we have two options, right? Two options. So let's say we put one of the X's that beat both LC symbols here in the first hand. So then there's K options here, right? And then now we can pick anything else for the second one because any of these hands work in beating LC. Because all Bessie has to do now is just pick the first hand to present, and she'll be guaranteed to win. And likewise, the second case is if we can, we put the hand that Bessie ends up choosing in the second hand, so there'd be K ways to do this. And the first hand can be anything we want. So that's N times K again, right? And the total number of ways now is 2 times N times K. But this isn't quite right? Because we see that there's some overlap here, right? There could potential let's say the hands that beat LC is like, let's say N equals 4, and then K is just like K consists of like 1 and 3. Right. So here we could have like had the hand 1, 1, right? Or 1, 3. But here again, we could have had like 1, 1, 1, 3. Right. So we see that there's some overlap here because theoretically the same hand, like after when we choose this K and we choose this N, we could theoretically choose a non another hand that beats LC here, and which would also be counted in this case. So how do we do this? We could subtract the overlap. So we can just do the overlap would just be both hands beat LC. These hands are counted twice, right? Because they're counted once in the first case, once in the second case. So the final answer is 2 times n times k minus k times k. Right. We can also get this another way. We can also just do each case separately, right? So one hand beats LC plus other hand beats LC. This minus k. Made it pretty unclear. Times k plus k times k. This is the exact same thing. Any questions about this one? No? If there's any questions, please put them in chat. Otherwise, I think I'll just continue the next one because I think this problem was overall like the problem statement is really complicated, but if you understand what the problem is actually asking for, I think it's pretty easy because it's basically just yeah, you just follow exactly what it wants, right? You just like find the overlap and you just do a little bit of math to finish it off. I mean, the math part's probably the hardest part of this. You just have to know a little bit of combinatorics and like how to like count overlaps and stuff. Honestly, I don't know why this subcase exists. I don't see any code that passes. Yeah, like I think this solution is pretty straightforward. Oh, I guess yeah, I guess the one thing like maybe counting overlaps. So counting overlaps is pretty easy to do in Eleven, I think as well. So I think there's not too much more to talk about for this problem. Okay. All right. I think I'm just gonna continue to the next problem then. Let me